Finally, we're going to study the epoxides, and we're going to look at the ring opening reactions. We mentioned in the introductory video to epoxides that they have two electrophilic carbons that are particularly reactive because of the angle strain here. And we're going to see that depending on if they're being attacked by a stronger nucleophile, often in basic conditions or at least strongly nucleophilic conditions, versus a weaker nucleophile, which is typically carried out in acidic conditions, we can have some different product outcomes. In this video, we're going to focus on the stronger conditions. When a strong nucleophile attacks the epoxide, it's going to come in, attack the electrophilic carbon, and then the ring sigma electrons are going to move up and the ring will open. And that's the driving force of the reaction because the angle strain here wants to be relieved. And then finally, the O- that's generated needs to be reprotonated. And so there's usually either H plus or water. Sometimes it can be from the solvent. We'll see cases of that later, where the O- can grab a proton to get the neutral OH group. If we had an epoxide that wasn't the same on both sides, we need to learn how we decide which carbon is going to get attacked. And in the case of the strong nucleophile, it's going to go through an SN2-like transition state. And since we know that transition state is very sensitive to steric interactions, the nucleophile in the epoxide ring opening under strong conditions will attack the less substituted side of the epoxide. And so you'll get only one product from this reaction. Now let's look at the stereochemistry. So say we have an equally substituted epoxide. You could get nucleophilic attack coming in. This attack takes place from underneath the epoxide bridge. And so you end up flipping the group here that was facing down. It flips up and the nucleophile is in the position here. Of course, since this is an equally substituted epoxide, you could have a 50-50 chance of it attacking either side. So we would also have to account for the product that would form from the attack on the right side. And we would end up having a mixture of products in the end. Here are a couple of specific examples. So say we have an epoxide like this, and we're exposing it to methoxide in methanol. And this is a very common way to present alkoxides. It's very common to have the alkoxide dissolved in the parent alcohol. So when you see this methanol here, it's just acting as a solvent. We're really interested in the methoxide being nucleophilic. Since this is an equally substituted epoxide, we're going to have an equal chance of the nucleophile approaching either carbon, and so we have to account for both pathways. Remember that it's going to come in from underneath the epoxide bridge, so to speak, and so in both cases we're going to have the nucleophile pointing down and the oxygen staying up as it was. Something that I should note though is where this proton came from. When you're in a protic solvent like this, at the end you can assume that the final deprotonation step, so say you have something like this, your nucleophile, the final deprotonation step is going to be proton transfer between these two. And so when you're in a protic solvent, it's going to pick up a proton from the solvent. And if you look closely, what we've actually generated as a set of enantiomers in this reaction, a rule of thumb that you might want to keep in mind is that if you start with something like this that's achiral, you can't get a chiral product. We would consider this product mixture overall to be achiral. So when you start with an achiral starting material, the product is either going to be a racemic mixture of some sort, or it's going to be a meso product. So that's something you can always check yourself on as we start doing more and more reactions. Here's another example. This time we're subjecting the epoxide to potassium thiol, and the thiol, the sulfur, is going to be the nucleophile. It's going to come in from underneath. There's no stereochemistry to worry about at this particular carbon, but the O- obviously is going to be left alone. It's still on a dashed wedge there, and DMSO is just acting as the solvent. Since we were not in a protic solvent this time, we were in DMSO, we have to add water to reprotonate this O-, and so the water is done in a separate second step. One final note is that we did start with a chiral starting material this time, so it was possible to get a chiral product. Even sometimes with chiral starting materials, of course, you can get racemization and so end up with an achiral product. But the only way it's possible to get a chiral product is if you start with some sort of chiral starting material.